So the next thing we need to take a look at is determining where a given function is discontinuous, given the formula. And we're going to be looking for those two things that we talked about at the end of the last video, places where the denominator equals 0, and at the end of a piecewise function. So first, we're going to focus on where the denominator equals 0. And I want to classify my discontinuities as removable or non-removable. Our shortcut we're going to use here is if the problem cancels, we're going to say that discontinuity is removable. If the problem cancels, it is removable. Specifically a whole. This goes back to earlier stuff with limits. If we could factor and cancel and then not have an issue anymore and not get 0 over 0, we've got a whole, a removable discontinuity. If the problem remains after simplifying, then it's non-removable. And specifically, it's going to be a vertical asymptote. So let me give you an example of this. Let's take a look at the function f of x equals x squared minus 9 over x squared plus 5x plus 6. We want to figure out where this thing is discontinuous. Well, the first thing you need to do is figure out what makes the denominator equal 0. Take a moment and figure out what values would make the denominator equal 0. I'm going to go do some factoring. I'm going to say x plus 3x minus 3 up top. In the denominator, I've got x plus 3, x plus 2. So I think I am discontinuous at, well, x plus 3 gives me x equals negative 3. X plus 2 gives me x equals negative 2. I'm discontinuous at those two x values. Now I need to classify these as removable discontinuities or non-removable. Well, simplifying, I can do some canceling like that, so I can cross that out. My discontinuity at x equals negative 3, after simplifying, that's no longer there. I removed that discontinuity. I don't have an x plus 3 in the denominator anymore, so I'm going to label that one as removable. The other one, x equals negative 2, well, that problem still remains in the denominator. I'm going to call that a non-removable discontinuity. Let's take a look at one more. Let's take a look at the function f of x equals the cosine of x. I want to figure out where this is discontinuous. Well, I'm going to go and I'm going to set the denominator equal to 0. And I don't actually have a denominator. I guess I could say this is over 1, but that doesn't really matter. There's no denominator here, so the denominator is never going to equal 0. So we can't be discontinuous anywhere. We have no discontinuities. Which actually should make a whole lot of sense if you think about what the graph of the cosine looks like. You can trace out that whole graph without picking up your pencil. No issues, perfectly continuous. If the problem cancels, it's a whole. If it remains, it's a vertical asymptote. Now, the other case. When we jump from one piece to another on a piecewise function, I'm going to call this at the end of a piece. No, never mind. Let me try that again. Where we jump from one piece to another, on a piecewise function. And there are three different things that could happen. As always, make sure you're pausing the video if I'm going just a little bit too fast for you. The first thing that could happen, I'm going to write this out in symbols and then we'll try to figure out what it looks like. We could have at that place the limit as x approaches c from the left of the function, equaling f of c, equaling the limit as x approaches c from the right of the function. Which means I'm approaching something from the left, which is going to equal the value of the function there, which is going to equal what I'm approaching from the right. If that's the case, we're perfectly continuous there. no discontinuities. We're perfectly continuous. Next, if the limit as x approaches c from the left of the function f of x does not equal the limit as x approaches c from the right of the function. So maybe something like this. Well, if that's the case, what sort of discontinuity do I have there? Hopefully you said non-removable. A jump is a non-removable discontinuity. Okay, it's a non-removable discontinuity. Or a jump. Finally, if the limit as x approaches c of the function does not equal f of c. So something like this. What sort of a discontinuity is that? Hopefully you said removable. A hole is a removable discontinuity. It's a removable discontinuity. And specifically a hole. To deal with any of this stuff with the piecewise functions, I'm going to go and I'm going to find three things. The limit as I approach my value from the left, the limit as I approach my value from the right, and the value right there. If they're all equal, I'm continuous. If the limit from the left doesn't equal the limit from the right, I have a non-removable discontinuity. And if the limit doesn't equal the function value, I have a removable discontinuity. I want to take a look at two examples. Let's take a look at the function f of x equals x plus 1 when x is less than or equal to 0, and x squared plus 1 when x is greater than 0. And I want to figure out, whoops, you can't see that, sorry. F of x equals x plus 1 when x is less than or equal to 0, and x squared plus 1 when x is greater than 0. I want to figure out where I have a discontinuity. Well, there are no denominators, so the only place I could have a discontinuity is at x equals 0, because that's where I jump from this piece to that piece. I don't actually know if it's a discontinuity yet. I guess I could be continuous there. So I'm just going to label this as a possible discontinuity. Possible discontinuity at x equals 0. Now I'm going to go and I'm going to find the limit as x approaches 0 from the left of my function. I'm going to find f of 0, and I'm going to find the limit as x approaches 0 from the right of my function. Well, when you're to the left of 0, what piece are you on? Top, middle, not middle or bottom, top or bottom? I hope you said top because of the less than part over there. We're going to plug 0 into that. I'm going to get 0 plus 1. I'm going to get 1. Right at 0, what piece am I on? The top or the bottom? Well, because of the or equal to symbol there, I'm on the top. 0 plus 1, I'm going to get 1. Limit as x approaches 0 from the right of the function. Well, when you're to the right of 0, you're on that bottom piece. You're going to do 0 squared plus 1. 0 plus 1, you're going to get 1. I actually don't have any discontinuities here because all three of those things are equal. I'm perfectly continuous. What I'm approaching from the left equals the value right there equals the thing I'm approaching from the right. I am continuous everywhere, including at x equals 0. And we might be asked why we're continuous, especially on like a free response part of an AP question, including at x equals 0, because, why are we continuous there? Because the limit as x approaches 0 from the left of my function equals f of 0 equals the limit as x approaches 0 from the right of my function. Just going back to my definition of being continuous. Let's take a look at one more of these. Make this one a little bit tougher. Let's say f of x equals, okay, x squared plus 2 when x is less than or equal to 2, 3x minus 1 when x is between 2 and 3, 5 when x equals 3, and 14 minus 2x when x is greater than 3. First thing I want you to do, tell me where our possible discontinuities are. Hopefully you realize that could be at 2, or that could be at 3. I have possible discontinuities at x equals 2 and x equals 3. So first focusing at x equals 2, we need to go find the limit as x approaches 2 from the left of the function. We need to find f of 2, and we need to find the limit as x approaches 2 from the right of the function. Go do all 3 of those and then submit your answers through Edpuzzle. Well, when I'm to the left of 2, that means I'm on the top, so 2 squared plus 2, 4 plus 2 is 6. Right at 2 is, again, using that top piece, 2 squared plus 2 is still 6. When you're to the right of 2, you're on this piece over here, so 3 times 2 minus 1, that's 5. Let's see, from the left I'm approaching 6, which is the value I have right there, but from the left I'm from the right I'm approaching a 5, which means I have a non-removable discontinuity at x equals 2. I do want to give the reason why. Non-removable because the limit as x approaches 2 from the left of the function does not equal the limit as x approaches 2 from the right of the function. Please make sure your reasons are when you're discontinuous are just two-part inequalities. It sounds strange to say this limit equals this value but doesn't equal this limit. Just tell me what does not equal what. Now we need to do the same analysis at x equals 3. Take a moment. At x equals 3, find your limit as x approaches 3 from the left of your function. Find f of 3, and find your limit as x approaches 3 from the right of your function. And go submit that answer through Edpuzzle. Let's see, when I'm to the left of 3, I'm on this piece, so I'm going to do 3 times 3 minus 1, 9 minus 1, that's 8. F of 3 is right over there, that's 5. So I already know I'm discontinuous. Limit as x approaches 3 from the right of f of x, I'm on the bottom piece, so this is 14 minus 2 times 3, 14 minus 6, that's 8. I'd like you now through Edpuzzle to tell me what's going on there. Well, let's see. From the left, I'm approaching 8. From the right, I'm approaching 8. But the value at x equals 3 is 5. I have a removable discontinuity at x equals 3 because, well, I'm just going to say my limit as x approaches 3 of f of x does not equal f of 3. So taking a look at those graphs of those last 2 examples that we looked at, that first one with just the 2 pieces in it, where x was less than or equal to 0 and greater than 0, and we found that it was continuous, here's what that graph looks like, and yep, this thing looks continuous everywhere. That second graph that we looked at with the 4 pieces in it, well, we said that we had a non-removable discontinuity at x equals 2, and that's what I see there, jumping from a height of 6, which I found in my work, down to a height of 5. Then I also have a removable discontinuity. Desmos isn't great with trying to show those. It's a little better than the graphing calculator. I do see that point over there at 3, 5. I have a removable discontinuity at x equals 3. Otherwise, I'm approaching 8 from both sides.